Hello everyone, I'm Kartik, PhD graduate from the University of Texas at Austin. In this video, I would like to give a brief about our recent paper on harnessing multimodal sensing for multi-user beamforming in millimeter wave systems. This work is with Professor Robert Heath at University of California, San Diego, and it has been recently published in IEEE Transactions on Wireless Communications. This work was supported in parts by NSF and in parts by federal agencies and industrial partners as specified in Resilient and Intelligent Next-G Systems program. In this work, we focus on multi-user millimeter wave communication system where the base station uses a hybrid millimeter wave antenna array. We know that beamforming is mandatory for millimeter wave antennas. The current commercial standards describe very straightforward method of beamforming, which is beam sweeping. For example, the 5G system defines the beam sweeping for FR2 bands as follows. For each beam, the base station transmits synchronization signal block. After covering all or some of the beams from the codebook, the base station gets feedback from all users and then it sets the beam pattern through RF precoder. Once RF precoder is set, a channel state information is captured by sending reference signals and then again receiving the feedback. Finally, based on channel feedback, baseband precoder is set and then data transmission begins. As expected, this creates a significant overhead. It has been shown that only beam search phase itself takes 80 microseconds. Combining that with the feedback and CSI acquisition phase, the overhead becomes significant. Therefore, a lot of effort from academia and industry have focused on optimizing this process. It has been shown in a lot of work over the last decade that for a traditional wireless networks such as Wi-Fi or cellular, we can design much more efficient beam sweeping methods. For example, we only showed a straightforward beam sweeping. However, the base station could use hierarchical beam search with a combination of wider and sharper beams at each level. Even more interestingly, one could also design an optimized codebook for each deployment based on the historical data of user locations and scatters in the environment. And not only that, in all these methods, one could introduce signal processing based methods such as compressive sensing or compressive phase retrieval or machine learning tools such as DNN and reinforcement learning as per individual's taste. While there are these ideas, the next generation wireless networks are going to have a very interesting feature, sensing. It is known that for many use cases, the next generation networks will have access to many sensors such as LiDAR, camera, GPS, and radar. Even though they are out of band, they give important information about the channel. For example, it has been shown that each of these sensors individually and various combinations of them can predict a prior on the angle of arrivals and departures of dominant paths, and they can also predict the existence of blockages. Therefore, the base station can only focus on the relevant directions or predicted directions for beam training and refinement. As a result, this reduces the overhead. While there is a rich literature, we realize that most of the solutions only focus on a single user setting. Moreover, the most work only attempt to predict the top k likely beams from that codebook. That brings me to the first contribution of this work. We show that those solutions that only tries to predict the beams from the sensor data for each user separately are suboptimal for multi-user communications. Consider the figure shown here. When the base station identifies the best beam for each user greedily, it does not account for potential inter-user interference. Not only that, it also does not exploit enough channel diversity. For example, consider an example from RAMOpt10 dataset. Here we show the beam space representation of the channels of two users. As we can see, individually both users have the chances of the highest rate when the beams are pointed along 135 degrees in azimuthal and 90 degrees in elevation. However, when communicating to both along the same direction simultaneously, it will inevitably introduce inter-user interference. Instead, if the second user can be served using other channel clusters, which may have little lower channel quality, base station can completely remove the inter-user interference and support simultaneous transmission to both users with potentially improved sum rate. Therefore, we argue that the base station must use a joint multi-user beam training strategy to support high-rate multi-user communication. In this work, we design a sensor-aided multi-user beam training framework in two stages. we first claim that the sensor data can provide the directions of channel's significant multipath components and not only the directions of the dominant channel paths. Specifically, in the first stage, given the multimodal data, a neural network can be trained to predict the directions of multipath clusters of the channels to each user. We then propose a multi-user precoding strategy that avoids beams to multiple users over same directions and therefore reducing the inter-user interference. This is then followed by standard channel state acquisition and baseband precoder design. To design this framework, there are three questions that needs to be asked. First, how should the directions of these channel paths be encoded to use as the label for the multimodal deep neural network? It is not a classification problem. We are not predicting the best beam out of the codebook. It is also not simply multi-label prediction problem where labels have no notion of similarity between them. There is an inherent similarity between different channels in terms of how close their multipath clusters are. Therefore, we have to design an encoding method that can maintain this notion of similarity. We design what we call hard and soft encodings of these multipath directions. The second question is how to train this model effectively. We can and we must exploit this inherent similarity between these channels. Specifically, we want similar channels to extract similar information from the sensor data. And to enforce this, in addition to usual binary cross entropy loss, we propose a novel supervised soft contrastive loss. It is a beautiful extension of supervised contrastive loss, which only allowed discrete labels. Instead, our supervised soft contrastive loss can be applied to the settings with continuous labels, and it can be applied to a lot of applications to enforce this contrast for training a neural network. And finally, once we know the directions of the channel paths, how do we determine the beams for multi-user communication that maximize the sum rate? In this paper, we have answered all three questions in varied details, and with all this, we have shown that this framework can improve the sum rate up to 4 times in multi-user setting compared to the single-user approaches that are applied in the literature. And to evaluate the performance, we use the RAM uptime dataset and design the simulation using 5G F new radios numerology for FR2 bands. We use the achievable sum rate of all users as the evaluation metric. The achievable sum rate of our framework is shown in the pink. The gold standard setting where the base station has access to a complete knowledge of the channel to all users is shown with the black line. This is denoted as full CSI setting. And the orange line represents the achievable sum rate using the single user beam prediction strategy, assuming that we have perfect prediction of the best beam to each user. We observed that at 42 dBm with 4 users, the sum rate of our proposed solution is 4 times the achievable sum rate of when using the single user solutions with perfect prediction capability. We also present the best case scenario of our framework in purple when the deep neural network model can perfectly predict the directions of all multipath components of the channel. With more research dedicated to the DNN model and its training, the pink curve can get closer to the purple line and can achieve similar sum rate as the full CSI setting. Finally, to summarize, in this work, we showed that the sensor-aided single-user beamforming solution is not enough for multi-user setting. We then showed for the first time that the sensors can provide the directions of the channel's significant multipath components. Finally, we showed that the joint multi-user precoding strategy is necessary to improve the system throughput and provided one way of using channel's multipath directions predicted by sensor data for such joint multi-user precoding. For more details on this work, check out our paper on IEEE Explore and Archive by scanning these QR codes. You can also check out the related works on security and management of wireless networks on my website at kartikpatel.in and more machine learning based optimization of 5G beamforming on Professor Heath's website, professorheath.org. Thank you.